and sharing the screen. It's Monday, the 18th. Okay, and let's take a look at the exam, right? Let's see, more students coming in. Let's see, we started on the 28th. And if we stick to this schedule here, the exam is going to be next week, Wednesday of next week. Okay. That's what were originally scheduled. And let's see, when is the second exam? The second exam would be a little bit after 1 month, right? And think about this date of the first exam. If you need me to postpone, we can do that. Maybe we could postpone it to this other week. Otherwise, we stick to this schedule, okay? So think about that. In case you. Yeah, that's right. We are going to do. Yeah, we are going to continue with the lab on Wednesday. Okay. So that was expected. Okay. At the beginning is a little bit more difficult because there are more than one thing that needs to be dealt with, like significant figures, right? But we'll finish that with one. We'll finish that on Wednesday. Okay. And okay, so that's the situation here. For now, the exam is scheduled for next week. Let's get to move here with the material. Okay, and so here you go. That's where we stopped last time, and we're going to get back to 1D motion. Okay. Today is the 18th of September, 2023. This is a Monday. Okay, and let's see where we stopped in the lecture, right? Let's see where we stopped in the lecture last time. This was the notes for the lab, Wednesday. And yeah, okay, we were doing some examples of one-dimensional motion, right? Like this type of problem, if you recall, we were looking at. I'm going to write that down there below. Okay, let's write that down here below. Last time we were doing some 1D examples, 1D motion examples. Specifically, the problem of intersection. Okay, that's what this problem is all about. Is one car catching up with another? Is one object catching up with another object? I call this type of problem the problem of intersection. Okay, and when one car intercepts the other, right? That's the simplest. That is the simplest type of intersection problem you will see in your lifetime. Okay, intersection problem. Intersection is a 1D intersection problem involving uniform motion. 1D intersection problem involving uniform motion. So, but you can extend this type of those problems of intersection have several other types. Okay, this is the simplest one that you're going to see, like I said. But there are several others. There are several others. There are several others more complicated types of intersection problems. Okay, one that we didn't get yet. We didn't get there yet, right? Intersection involving 1D intersection. 1D intersection involving uniformly accelerated motion. Okay, so instead of uniform motion, constant velocity, now you have the objects that are accelerated. And then you can go for 2D interception involving uniform motion, right? You can have 2D intersection involving uniformly accelerated motion. And then you can have all sorts of problems, even far more complicated, that are used in the military. Think about the Patriot missile system. You go Patriot missile system, okay? If you're in the military or if you follow the news, you know that, and the Patriot is Patriot is the American one, but there is also the Jewish one, as we call it, the Iron Dome missile system. This is the US, right? And that's the Israeli. So there was, there's some discussion whether Israel could send the Iron Dome system there to Ukraine, protect the Ukrainians. The Ukrainians already have the Patriot missile system there, right? To intercept the missiles from the Russians. The Patriot system was initially used in battle. Please correct me if I am wrong. Someone that's in the military knows that better than I do. I would say that the first time the Patriot missile system was used in a real battle space, right? It was during the Gulf War, the first Gulf War. Okay, and it was a big back in the 90s. Okay, it was a big thing about that time. The press was reporting all sorts of successful interceptions made by the Patriot missile, and the U.S. at that time even sent a battery of Patriot. I don't call it Patriot missile. I call it Patriot anti-missile. Would be a better way of characterizing that. So the US military sent a battery of Patriot anti-missile to Israel because Saddam Hussein was bombarding Israel. There was even a missile, a Scud missile from Saddam Hussein that reached Tel Aviv. Okay, and the Israelis were, they want to bombard the Saddam Iraqi, right? Saddam Hussein, and the United States, no, don't get into this war. It's going to become too complicated, and the Israelis had to restrain themselves. It's a really touchy situation. How can you tell someone not to attack someone who use aggression against you, right? That's what the US was telling the Israeli at that time. So there are different types of, and there is also the case of rocket ship, docking with the space system, this International Space Station, ISS. Okay, that's another type of intersection problem, but it's a far more complicated intersection problem. A far more difficult intersection problem. This, in this case here, all you have to do, you want to hit the missile. In the case of the Patriot missile system of the Iron Dome missile system of Israel, you want to hit a missile that's in flight. It's not just a missile; it can be a bomb as well that's dropped. Okay. And all you have to do is, hit it hard enough to destroy the missile or the bomb. But here is a far more delicate process. You do not want a rocket ship to hit the space station and blow it up. No. To hit the space station is a far easier problem than to dock it with the space station. When you want to dock with the space station, you want to adjust your velocity, your approach at very low speed so you can safely dock with the space station. Okay. Now in this case here, is those cases that you see here are far more easier problem than this one. Okay. So that's what those problems are all about. Those are intersection problems. So if you're going to the military on the future, if you are going to work in military project, you might get involved with something like that, how you're going to adjust your vector velocity, right? How you're going to adjust your fuel to intercept an enemy missile. It's also, what you see here is far more difficult than what we're doing here in class. But of course, that's a level of increasing difficulty, right? Some post to more difficult problems to solve mathematically. So all those equations that we are deriving here is the starting point to reach here and here. Okay, so the Patriot missile has a computer there that keep on adjusting its trajectory of the missile so you can of the anti-missile to hit the missile, right? That's what we have. And let's see what else we saw before. Let's see. That's the intersection problem, right? Okay, I started defining acceleration, right? But I didn't get into the equations of motion for acceleration. So let's do that now. Okay, so I defined acceleration and then got into the problem of intersection. And there, hockey table, real life, let's take a, okay, so here one. The average, okay, here you go. That's the equation of motion for uniform motion for constant velocity. And let's take a look now at the equations of motion. Equations of motion for uniformly accelerated motion. And let's go back to our definition of acceleration, because we're going to need that. We go here, right here. Yes. Okay, let's look at this one here. Right? Those are the equation. Those are the definitions of accelerated motion. Those are the definitions of acceleration, right? Average acceleration first, instantaneous acceleration afterwards. Okay. And that's the starting point, is the definition. Let's get into the equations of motion, right? When I mean get the equations of motion, what do I exactly mean? I want to get, going back to what we did before, right? The steps are very similar. Here you go. The steps that we're going to take are very similar to the step that we took for uniform motion, but it's going to end up being a little bit more complicated. Here you go. That's what we mean when we want the equations of motion. What do we want? We want x as a function of time, v as a function of t, and acceleration as a function of h. Okay? And I don't want to. Okay, so our starting point is right in here. In uniformly accelerated motion, we have the following. We have that A is constant. Okay. We have that A is constant. And if A is constant, the average acceleration is going to coincide with this instantaneous acceleration, right? If A is constant, from this definition, we can state that the average acceleration is equal. Average acceleration is equal to the instantaneous acceleration. So we use our equation of average acceleration, write that down as being equal to the instantaneous acceleration. I'm going to, spell out what delta V is, right? Remember that? And then I'm going to spell out what delta T is as well. Your TF minus T naught. And now we go ahead and do our simplification, right? Every time that you see VF, we just simplify the notation. So you don't keep on carrying too much stuff as being just V. VF is going to be equal to V, the nickname of VF, right? V is the nickname of VF. And similarly, the nickname of TF is going to be T. We do that to save on the amount of force, but we cannot do that here for V naught and T naught, right? We cannot do that for V naught and T naught, because if we do that, we won't be able to distinguish the final velocity from the initial velocity. We have to keep it that. Another important, another important simplification is to adjust, okay, the origin the origin of our t-axis. Okay, we are going to choose the t-axis in such a way that its origin coincides with the initial instant of time t naught, or like that, italicize to make it look nicer. Okay, so when we do that, we make t naught equal to 0. Okay. When we do that, comma, t naught becomes 0. T naught becomes 0, or and now I am calling the average acceleration just a, right? And the next step is just going to be something like that. Here you go. Remember that we have 3 equations of motion, right? That we have to find. The first one we already found. The first equation of motion is in reality the last one that we wrote that down here. A is not a function of time in this specific case, right? But there are cases in which the acceleration is going to be a function of time, but this we didn't get there yet. Okay. Now what we have to do, we already have this last equation here, one of the equations of motion, and now we're going to find this equation of motion here. We're going to find this equation. I'm going to even highlight it here. Yeah. How do you do that? All you have to do is to solve for V. Oops. Solve for V. Right? And we're going to the next step downstairs here. Okay, I'm going to pass the t to the left side. And then we're going to isolate v. V becomes v naught plus at. And that's our second equation of motion for the case of uniform acceleration. Okay. So I'm going to take the boldface out of the equation, and now we're going to concentrate on this equation here, on this other equation, x as a function of time. Let's see how it looks like and how we do that as well, right? Okay. How do you solve the equation for x, right? We go back to find the third equation of motion. We use the definition of average velocity. Okay, and I'm going to copy that here because the equation for average velocity is very similar to the equation for average acceleration, right? The only difference is that the velocity is changing in time, and we cannot say that the average acceleration is equal to the average velocity is equal to the instantaneous velocity. Okay, and we also have to change v to x, right? It's not much different than what we did before, but it's just a little bit complicated, okay? And replace v with x, right? The delta t we leave this way. And then we simplify our notation again. Okay, so here we go, x naught. And we do the next step, make t naught equal to 0. Right? And we are almost there. Now, in the next step, we do something that we didn't do. In the next step, we do something that we did not do for the case, for the acceleration, right? For the equation of motion. For the acceleration, equation of motion for the velocity, okay? Equation of motion for the velocity. We use another definition of average velocity. There are two definitions of average velocity, which you should be already familiar with, right? And I'm going to write that down for you. So here you go. Don't forget there is another symbol for average velocity too, in case you see it in a different way. Okay, let's see here. I think it's bar. Nope. No. Some books adopt a different notation for the average. No, it's not what it is. So let's see here. It's the other one. Here you go. Let's do this one. Yeah. It's a bar at the top of the V. Okay, it's a different notation, but which means the same thing. You either use V average or use V bar. Many books prefer to use this notation here. And there is another definition of average velocity, and you should be familiar with this other definition. Okay, so this other definition is final V plus initial V divided by 2. Are you familiar with that? Simple enough, right? Dropping the subscript F, we end up something like that. And recall that we don't want to find the average velocity, right? We don't want average velocity in our equation, right? We want the final velocity or initial velocity in our equation. And with this definition, we can go ahead, make what you have, this term here, equal to this term. I'm gonna emphasize that. It's a little mathematical trick that we do in physics. Very useful mathematical trick, right? So now we have two equations for the average velocity. Those two equations are both very useful. Okay, they are both correct. They look different, but they are both correct. We have those two equations for average velocity. What do we do next? Okay, we go ahead. I'm going to copy and paste it here. I'm going to copy this other definition of average velocity, and I'm going to plug it here. And I can now remove the boldface. Okay. And note, see that now what do we have now? We have this exposition, right? The equation of motion for x, we might be able to get from here. It seems that we can get it from here, right? And I'm going to highlight it again. Boldface here and boldface here, right? We want to find this guy. And we have this V here, which, by the way, we have already found how it looks like. It looks like just like that. Okay, I'm going to boldface it. See that? We are going to be using previous results in this equation right in here. So let's get there. The first step is to substitute what we found before for the final velocity right here in this equation. And now I'm going to remove this boldface. I don't need this boldface anymore. And note that we're capable of simplifying this equation, the right side of the equation, because we have V naught here repeated right in here, right? Let's simplify that. The key in those derivations is to try to simplify as much as you can. It comes to a point that you cannot simplify anymore, okay? And that's what we have so far. Let me do something else. I'm going to, I'm going to take this V naught outside the division sign, right? That's what we have so far. And x minus x naught, here you go, like that. That's what we have. I'm going to take out the boldface here because we don't need that anymore. And now what we have to do, we have to solve for x. We have to get our last equation of motion. And we do that by passing the t to the other side, right? Here, I'm gonna put the t upstairs, multiplying my other t. When I do that, okay, here you go, 1/2, and here we get t squared. Eliminate the other t. We do not need the 2 downstairs, right? Because we already wrote down the half in front of it. And we go for the final step. The final step involves passing the x naught to the other side. Okay, and here you go. I'm gonna put an equal sign here. I'm gonna put a plus sign here, and we have our final equation of motion that documents, predicts the position of an object that is uniformly accelerated. An object undergoing one-dimensional motion and which is also uniformly accelerated. Let's copy everything that we had before. We get those other 2 equations that we need. Those are the 3 equations of motion. And I can even come up with a table to summarize everything that we got, something like that. Equation of motion 4. Uniform motion, uniformly accelerated motion. Okay. Here's the A, V, and X. I can italicize them. Okay. I'm gonna put it in a better way here. Design the table, not this one here. I'm gonna do something like that. Instead of what I want the difference of 0 sign. Here you go. Difference of 0 sign. Better, right? Okay. If you have a hard time, and there is one more equation, let's see. I'm going to put another equation right in here that was very useful in the derivation of this one here. Okay. (9:30). And now we have to start looking at how we represent those equations of motion in a graphical format, right? So here you go. You have to know what that the graphs for uniformly accelerated motion. Like that, graph for uniformly accelerated motion. A versus T versus B versus T, B versus T, and X versus T. How do they look like? I have them right here. Let's take a look. My PowerPoint presentation. Not that I want. Let's see. That's not good. One student coming in. Let's see. Okay, let's see if we can get search. Okay, I think I'll have to go do that manually. Let's see. I'm looking for my illustration, which are right in here. Okay, let's see. Go. And so let's take a look. You already saw that those slides, right? And okay, you saw those graphs. X versus T for a positive velocity. Positive velocity means that the velocity of the object is along the positive direction, right? We did that before for uniform motion. That's for uniform motion. And I'm going to repeat that, but for the other parameters, see if I have here. Okay, yeah, let's put it here. First, let's start with acceleration, with acceleration. Okay. Okay, the acceleration for uniformly accelerated motion is going to be something like that. And instead of A naught here, we write down as being A naught to distinguish from A, right? Constant. Uniformly accelerated motion. Acceleration is different of 0. And I'm going to Huh. Okay. Uniformly accelerated motion. Accelerated motion, like that. Our next graph is going to be something like that, but with a different y-axis. It's going to be linear, right? That's what my equation here tells us. The velocity is linear with t. If the acceleration is positive, then the slope is going to be positive as well. Okay? And here what we have, we must have a v naught, not x naught, but a v naught. Here's t. I'm going to put here, I'm going to put like that. Let's say v naught is positive. The next graph is going to be a little bit more difficult. It still is going to be x, okay? But let's say I'm going to put x naught right here, but it's not going to be a straight line. Let's go back to our equations. It's going to be a parabola, right? A parabola right in here. And let us see if I can draw a convincing parabola here. I'm going to try this one here. Let's see. Yeah, here we go. Like that. Okay, here you go. Yeah, it started looking like a parabola, right? Let's see if I can go up a little bit more. Yeah, sort of a parabola. Okay. In this specific case, you have a V naught that is less than 0. But if I want to make a V naught greater than 0, all I have to do is to flip this parabola, right? There you go. X naught is greater than 0. V naught in this case is greater than 0. But the acceleration, I can tell you right now, the acceleration in this case is negative. The acceleration is negative because the concavity of the parabola is downwards, okay? If I want to put an acceleration that's positive, I have to switch back the parabola, right? But if I want to have a positive initial velocity, it should be something like that. Okay, we can play with Excel to come up with all sorts of different conditions for your graph. Let's see. Yeah, great. So here you go. Let's, shorten this axis, right? So you can parabola. That would be a parabola. Let's see if I can do something else here. Yeah, and I'm gonna do like that. Uh-oh, what did I do? Interesting. Oops. I'm gonna do something like that. Here you go. Yeah, that's what I want to do. I'm gonna shadow this guy, but I'm gonna do even more. I'm gonna shorten it. Oops. Oh yeah. Okay. Okay, can do better than that. I want to shorten this one like that. Now I can superpose. I'm superposing it because I'm just showing to you what happened. What happened to this parabola on the left side of, on the negative side of t, right? That's all I'm doing. Yeah, well, let's leave this way. Let's not struggle with that. Do you see what's happening? Okay, that's X position, right? Oops, go up. And that's T. In this case, here go. A is greater than 0. Acceleration is greater than 0. I'm gonna need this guy. In this case, you know, VA naught, A is still greater than 0. Oh, look back. Let's go back here. Here you go. A is greater than 0. And what else? And V naught is also greater than 0. Okay? Because the origin is right here. Let me put my A downstairs here in this. Let's see if I can. Subscript. Play a little bit is that. Let's see, greater than 0. Yeah, didn't do it. Let's see. Okay, now I should V naught greater than 0. Right? I'm going to italicize to make it look nice. Italicize this one here too. Italicize this one. Italicize this one. Italicize this one. I don't need that. Okay. A is greater than 0 because this slope is positive, right? And V naught is greater than 0, which is the intercept. The intercept is above the origin. And I'm going to label here the origin 0. I don't want the 0 italicized. I'm going to put the origin there of my acceleration graph as well. I prefer a little bit higher. And I'm going to, just to make it look nicer. Here you go. Just to mirror what the next graph looks like. Right? Here you go. And next step is this one here. I did everything that I could have done to give you the illusion that this thing is a parabola, right? And let's see. Yeah, I can mirror what I have here as well. And I'm going to need those two boxes. Right? Copy and paste here. I don't need this one anymore. But I can shorten that. Yeah, I'm gonna shorten it even more. What else can I do here? Okay. X naught greater than 0, right? X naught greater than 0. Okay, 1, 2, and 3. Nice enough. I'm going to, yeah, I'm going to use the same axis here. Okay, uniformly accelerated motion. But then you can have different situations, right? Let's see. 1, 2, and 3, right? Everything is positive. But what about if the acceleration is negative? What about if the acceleration is negative? How would this axis look like? This axis, oh, this axis would look like the following. Move up. Like that, right? And now if the acceleration is negative and the V naught is positive, if the acceleration is negative and the V naught is positive, let's put here V, right? We are going to have something like that for the velocity. And I don't need to display that. I'm going to copy this. I can, let's see. Yeah. Okay. And the next step, I don't need that anymore. Oh, I need those two, right? Copy that. Just this one, not this one, because the acceleration is negative. Now we want to do the next graph. For the next graph, my parabola must have a concavity down because the acceleration is negative. Can you remember that? Concavity down. Let's see, velocity, initial velocity is positive, right? I'm going to pick up initial velocity is positive. What means initial velocity is positive? The slope must be positive at this point at t equal to 0. Okay? Since the acceleration is negative, the concavity is down. And I'm gonna get here x naught greater than 0. Okay. Let's shrink it a little bit more so it appears more like a parabola and less like an egg shaped, right? Like that. Okay. That's one possible. That's another possibility. And then you have all sorts of. Eric, turn off your camera, please. Okay, would look like, give the slope at time t equal to 0 is positive. Consequently, the velocity, the initial velocity is positive. Oh, I gotta change it here, right? Gotta change it here for x naught. And what else do I have to do? Yeah. Here should be just meter. Like that. And 947. And then you can start thinking about how the other graphs would look like, right? I did just for A positive, V not positive, and X not positive. I did and A negative, V not positive, and X not positive. Oh, let's see here. Okay, this one, it's not supposed to be here. So you can start thinking how it look like for A positive, V not negative, X not positive, right? You can start thinking how it looks like for those cases and many others, not just those. That's what we have for the equations of motion. Let's go back here and okay, here you go. A versus T, okay. Oops. And let's go for our attendance. Let's see. Any questions? Let's see. For it. Okay, I'm going to do better. I'm going to do easier. Wait a minute. Let's see who's coming. Eric. Okay, thank you. Roster. Okay, today is the 18th. Okay, 11 is here. Okay, now let's cut. Oops, nope. Oops, no, I want insert here. Good. Let's go. Sky, are you there? Sky.
Yes.
Okay, thank you, Sky. Next one is Tessa.
Yeah, I'm here.
Okay, thank you, Tessa. Destiny. Hi there, Destiny. I'm gonna put Destiny is here, but I don't hear from her. I'm gonna put a star. Let's go, Gael. Gael Garcia. I don't see Gael. Okay, next is Ridwan. Ridwan is here. Okay, thank you, Ridwan. Next, Ashley Izomo. I don't see Ashley here. Next in line is Norberto. I see, I've never seen. You're there? Okay, thank you, Norberto. Annabelle Madrigal.
I'm here.
Thank you.
I was also here last week too. I see a star next to my name.
I didn't understand. What did you say?
I was also here on Wednesday too. Last Wednesday.
You're here on Wednesday. Oh, this is Monday.
Oh, whatever it was.
Okay. This is Monday. Okay. Eric Martinez.
I'm here.
Okay, thank you. Vanessa Mena.
Here.
Thank you, Vanessa. Nazmoon. Destiny. Okay, thank you, Destiny. I don't see Nazmoon. And Catherine Pacheco.
I'm here.
Thank you, Catherine. Camden Park. Hello, Camden.
Yes, I'm here.
Thank you.
Yeah, I'm sorry.
Thank you. Vitória Preciado.
Here.
Thank you, Victoria. Alexis Richardson.
Here.
Thank you. Donovan Robinson. Let's see, Donovan didn't come, right? Yeah. And Marco Sanchez. Thank you, Marco. And next is, see, that's 13, right? We should, okay, looks like we have 13 students. We have, oh, wait a minute, we have 13 students. Yeah, okay, we counted 13 here. That's good. Looks like everybody is here. 9:55. Any questions? Have you thought about the exam? Right, let me just remind you. Right now, the exam is scheduled for the 27th. And when is the 27th? The 27th is the Wednesday of next week. Okay, we still can postpone it for 1 week. Okay, if you prefer postpone another week, we do it. Otherwise, we keep it as originally scheduled. Okay, and we're still doing 1D motion. Okay, and if you don't have any questions, let's go for our break. It's
Professor,
yeah.
did you say you're going to postpone the first exam next, like another week?
Yeah, I could postpone for one more week.
One more week?
Yeah, if
Okay,
you
very nice.
if you prefer, we can do that. Otherwise, we keep this schedule. We'll make a final decision on Wednesday, right? Let's make a final decision on Wednesday. And then I ask you one by one whether you want to keep the exam for next week or not.
Okay, thank you so much.
Okay, so at break, that's 9:55 a.m. to 10 a.m. Okay, and I see you in 15 minutes. Hello, folks. I'm back here. And let's do an example. Simple numerical example. Okay, and here you go. Okay, right in here. Example of uniform motion. Let the car have an acceleration of 1 meter per second square along the positive x-axis. The initial velocity and position are 0. Do the following. 1, write down its equations of motion. Okay, this is a very a much simpler example than the generic formula that we have. Okay, notice the initial velocity is 0 and the initial position is 0, right? So write down the equations of motion. Plot the acceleration versus time for this instant of time, right? Velocity versus time and the position versus time, right? Try to see if you can do that, if you can solve that on your own. Write down the equation, the 3 equations of motion. I have a uniform, let's put here, uniform acceleration. Has a uniform positive, right? I'm going to emphasize of 1 meter per second square. So we're going to put here plus. So write down the 3 equations of motion, and then we're gonna plot, okay, all those three graphs. We're gonna plot using Excel. In Excel. Yeah, it's okay to do in Excel. Yeah, it's okay to do in Excel, but you can do by hand or each, whatever way you choose. Okay, can be Excel, can be PowerPoint, can be in the paper. Okay, so it's up to you. Okay, let me give you, I'm gonna give like, let's see, we started. Let me give another, I'll give until 10:20, okay? Try to solve it before 10:20. Try to solve everything before 10:20. Hmm. Good. Okay. Going back to our notes. Yeah. And 10:20 already. Right, so the first step here. The first step here is to write down what you know. That's the first step. Okay, so part one.
Professor?
Oh yeah, I gotta share the screen. Thank you.
Yeah, thank you.
Thank you. There you go. What's going on here? Here you go. Now we have it. Part one. You know, write down what you know. What you know in a mathematical way, right? So what you know is the acceleration. You know the initial velocity. Okay. You know the initial position. You also know that the motion is uniformly accelerated, right? Since the motion is uniformly accelerated, the equation of motion is going to be something like that. 1, 2, and 3. Right. Here we go. In this case, I'm just going to repeat the value of the acceleration. That's all. All right. The 3 equations of motion. We're not done yet. We're not done yet. We're going to be done whenever you substitute all those 3 values in those 2 equations. Okay, the first equation of motion we already know, right? What you have here is the equation of motion for the acceleration, right? And here I'm just repeating it. This is not the equation of motion for the velocity. This is not the equation of motion for the position. Those are just the initial conditions for the position and the velocity. Okay. The final equation of motion here are the genetic equations of motion for the position and the velocity. And the final equations of motion for the position of the velocity are going to be obtained when we substitute those values, all those 3 values, into the 3 equations, right? So let's do that. Part 1, x naught is 0. So I can erase, and v naught is 0. So I can erase everything. And v naught here is 0. There is nothing that I need to do here. But here we have to do something. Okay, so here we go. The acceleration is 1 meter per second square. Okay, make it look nicer by putting it right here. Many books omit the units because it's very cumbersome to keep on carrying the units all over the place, right? But the correct way, the strictly correct way, is to include the units there. This one, we do not need to keep it there. And, right? And that's what we get for the equation of motion for the x. I'm going to repeat that in a nicer way very soon. And then we do the same for the velocity. The acceleration is 1 meter per second square, right? And let's see, can we do better than that? Yeah, we can remove this one, right? Don't need to carry the one around. So unstable. Can you still see me, folks? I got a message here that my connection is unstable. Still here? Okay, good. Thank you. Okay, and now I'm going to just repeat what you have there in a nicer, in a cleaner way. Okay, and that's gonna be like that. Maybe we might want to put the units to the right of t. Yeah, we should put the units to the right of t. Notice that t square has units of second square. So when you substitute second square here, the second square cancel out with this other second square, and you end up with the single unit right here, right? In meters. So dimensionally speaking, from the dimensional point of view, this equation is correct. That's this one. I'm going to put the units also after the t. T has units of second, second cancel out with second square, so you end up with a unit of meters per second, and that matches what we have for the unit of the velocity, right? So those are the three equations of motion. Okay. So the next one, plot the acceleration versus time for t equal to 0 through 5. I can do that in PowerPoint. This one is the first one is a very easy one because the acceleration doesn't change. Okay, I'm gonna do that in PowerPoint, and by the way, I already have it. This one here, see this graph that I plotted before is exactly the solution to that problem. And I'm gonna paste it here, example, right? I'm gonna put it 5. All I have to do is 5. No, 5 no, it's 1, right? 1. And by the way, I said from 0 to 5 seconds, right? 0, yeah, 0 to 5 seconds. And now I gotta put the scale right in here. Okay, let's see if I can do that. Yeah. Scale, let's see. Rotate this guy. I'm not gonna rotate, it's too much trouble. Okay, just rotate like that. Now I wanna evenly spaced, right? 5. Oops, get what happened here. This one. 1, 2, 3. 1, 2, 3, 4, 5, right? If I want to put more, 1, 2, 3, 4, 5, I'm going to put 5 here. But I want the graph to be plotted only from 1 to 5. 1, 2, 3, 4, 5. Since it's already in seconds, since I already put seconds here in parentheses, I don't need to put the unit next to this number. Okay, 3, 5, 6, 7, 8, 9, right? The next one should be 10. Since this one is the easiest of all, I don't need to use I don't need to use Excel to plot it. And I'm plotting only from 0 to 5 seconds, right? So take out. If you are in the lab, you shouldn't leave this space in blank, right? So let's do that. I want to do it exactly the way I asked you to do in class. And then I'm going to do like that, I'm going to change the scale. Here's 1. Here's 2. Here's 3. And everything in between is the half. 4. And 5. And now I can extend this line. I change the scale, right? Like that. The next graph should be the V versus T, right? Isn't that nice that we can reuse, right? What we did before. So here you go, A is greater than 0. The slope is 1 meter per second square. And I'm gonna use the scale here that I created before. Okay, everything fits nicely. A is greater than 0. V naught is equal to 0. They'll keep on changing those fonts here. Sometimes it's really annoying. Okay, V naught in this case is going to be 0. So I don't need but because V is equal to 1 meter per second times t. So whenever you have t equal to 1 second, you're going to have a velocity v equal to 1, right? If you're doing, like I said, if you're doing that in Excel, Excel will do that automatically for you. Let's see if I can get it right. Right in here. No. If I extend like that, 1 meter per second is going to be right in here. Right, and then copy and paste. One. And now I want everything to be nicely, evenly spaced. What do I do if I'm doing this PowerPoint, right? I go through the trouble of doing that. If you're doing Excel, you don't have to worry about that because Excel is going to do that automatically for you. 1, 2, 3. One, two, three, four, 5. 1. Let's make sure we have the proper slope. 2, 3, 4, and 5. Let's see if I have it right. 2. It looks like I got the slope right, huh? Yeah, see that? I got the slope right. So I don't have to worry about that. Okay, that's how it looks like. And then I'll show you how to do in Excel. Right, and let's do now in order, let's see, that's acceleration, that's the velocity. Now in order to do that nicely, you have to use Excel, but I'm gonna do PowerPoint first. Because we're talking about a parabola here. X naught is equal to 0. V naught is equal to 0. I see you keep on changing to uppercase V. It's really annoying that Excel does all the time. Okay, so here you go. So what I have to do, I have to bring down my parabola here. X naught. No, I'm gonna keep the dash here. Okay. And I want to make sure that this parabola has a slope of 0 right in here, the origin. Okay? Because a slope of 0 right in here, the origin means initial velocity is equal to 0. Okay? And I'm going to go make it make a little bit thicker, but I don't want dashed. I want to do like that. Go a little bit higher, right? And let's take the right here. Right here. Oops, not what I want. This. At t equal to 1 second, you should have half of a second. So it looks like you have half a second here. Right? If you substitute t equal to 1 second, you should, not 1 second, 1 meter. Should have 1 meter, 1 meter, no, half of a meter. So it looks like we have half of a meter here. For t equal to 2 seconds, you should have 1 meter. 1 meter, let's see if it coincides. Now it's too high, my parabola is too high, right? Oh, no, sorry. It's not, let's do that again. Going back here. Is t equal to 1 second is half meter? Is t equal to 2 seconds is going to be 2 meters because 2 squared is 4 divided by 2 is 2. Okay, so it should be 2 meters. Let's see if we can get it right here. Right, go. 2 meters right here. That is 2 meters. Right here. Meters. And what do we do? We're going to shrink it a little bit. Yeah, right? The 2 seconds. Yeah, we got it, right? It looks like we did. Move a little bit. Yeah, like that. 3 seconds should be 9 divided by 2, which is 4.5. I'm going to shrink that. Okay, 3, 4, right? 5, right here. 1, 2, 3. Five, right in here. 3, let's see, 3 seconds, vertical. You know, I'm doing it in the hard way, remember? At my time, we used to do that by hand, not with software. So 4.5 should be around, I'm gonna just eyeball here. And then we do that with Excel. Okay, so the actual point of the parabola should be here. So this is not exactly a parabola, okay? That's why I cannot fit it nicely. Let's see if I can go. But if you want to fit it nicely, yeah, I cannot do better than that. Let's do in Excel. Let's do in Excel, right? Oh shit, right in here. Okay, bye-bye. One more. I'm gonna zoom in. I'm gonna put it here, A, meters per second square, right? V naught meters per second, X naught meters. Superscript, subscript. Nope, subscript, let's see. Yeah. It's too much trouble, so I just copied and paste what I had for V naught, right? here is 1, here is 0, here is 0. And then I have, I need my equation for the final velocity, and I need my equation for the position. Right in here, we go like that. And we go ahead, write down the equation, which is, oh, I need one more thing here before I do it. I need to put the t here, right? Don't forget t. I'm going to start with 0 seconds. I'm going to go by every half of a second until I get to 5. And then we write down the equation for v. The equation for v is what? Half times a times t is, oh, no, sorry. This is the equation for the position, right? A t. Okay, now for the position is what? X naught. And by the way, I'm gonna be even more complete here. Okay, instead of just putting AT, I'm gonna make sure I include V naught here. V naught plus AT. Okay, even though V naught is 0, I still wanna keep it there. And there's a reason for that. Okay, so the reason we're gonna see very soon, X naught plus V naught times T plus half A times T squared, right? Okay, any questions so far? So here you go, I'm gonna click those 2 cells. I'm gonna click and drag. Oops, it didn't work. Yeah, I know why it didn't work. And the reason is that B must be done with a $sign. A must be done with a $sign. We do the same here. C must have a $sign here. A little trick from Excel, right? A trick that's very well documented in Excel, by the way. Okay, once I do that, now I should get the right result now. Yeah, now I got it. Let's put everything with, let's see, how many? 1, and let's put just 1 decimal place here. I'm not worried about significant digits, okay? But I want to make sure that those numbers look nice. I don't need more than 1 decimal place here, but here I might need 3 decimal places. Again, I'm not worried about significant digits. I'm just worried about doing something that's going to look nice. Okay. And I'm going to do the following. I'm going to do something else too. Since we have to plot the graph for the acceleration, I'm going to put the acceleration here as well. Okay, and I'm going to put just 1 decimal place. Okay, and if we plot that for the acceleration, you get exactly what I got in my PowerPoint, right? I'm not gonna put the axis here. Okay, here you go, V and T, how does it look like? Insert graph, just a straight line. Okay, you can put the equation as well, right? Trend line exhibit the equation R squared is gonna be exactly 1 for this one, right? And the next one is X. We have 10 points, 11 points actually. Insert graph. Okay, now it looks more realistic, right? I don't need that many numbers. I don't need that many. Yeah, I don't need that many either. But that's your parabola. I can even put a trend line if I want, right? You're gonna get exactly that trend line, and here you go. Hey, wait a minute. Yeah, the trend line that we want to use in this case is not this linear trend line, it's the polynomial of order 2 trend line, right? Here's my half t squared, right? This x squared means the t. This one is close to 0. This one is close to 0 as well. It's just a rounding error of the computer. Okay? 10 to minus 15 for every, practical result is 0. 10 to minus 14 for every practical result is 0. So that's the tricky one that we cannot do, that we could not do in PowerPoint. Parabola. And the nice thing about Excel, right? Why is that? Why did I want to? Remember, I wrote down the whole equation, even though the terms were 0. There was a reason why I did that, right? The reason I did that because now I can start doing some simulations here. Okay, suppose their acceleration is equal not to 1 meter per second square, but 2 meters per second square, right? Oh, let's see. No, let's keep 1 meter per second square. Suppose the velocity, initial velocity is 1 meter per second, right? When I do that, it didn't do anything. Why is that? The graph was supposed to shift here, but oh, it shifted here. But why it didn't shift here? Let's see what's going on here. Oh, let's see. Yeah, the position should be 0. Yeah, the position should be 0. Okay. Yeah, the graph here is okay. Yeah, there's nothing wrong with this graph, but this one shifted, right? You can see it shifted to 1 meter. Now, this one's gonna shift if you put x not equal to 1, right? You're gonna shift like that. So what changed here in this graph what changed here in this graph, right? What changed here in this graph when I change it from 0 to 1? Watch this graph closely. Okay. What changed here is going to be the slope. What changed here in this case was the slope. Okay. That's what happened here. The trend line equation didn't update, by the way, but that's how, unfortunately. Yeah, see, the trend line equation doesn't update, unfortunately. Oh, yeah, now it updated. Before it didn't. Now it updated. If I go to 0, right? Here you go. We get this term here that's 0, but if I go to 1 here, right? Now it didn't update it. Sometimes it updates, sometimes it doesn't. It's a shame, Yeah. You remember that it updated before? Yeah, now it doesn't update. What a shame. Sometimes it updates, sometimes it doesn't. Let's see here. Yeah, now it's updated. I'm gonna put x not equal to 1. Yeah, it should change it. See here the position in the x-axis, the parabola was raised a little bit, right? And then you can keep on playing different values, right? You might want a negative acceleration. Let's put a negative, but if you have to put a negative acceleration, remember I'm plotting. Let's see this one here. Yeah, okay. Let's put a negative acceleration here. Okay. But the graph didn't update, unfortunately. What a shame. It's supposed to update the graph. I don't know why. Not even the equation updated. Sometimes it does it, sometimes it doesn't. What a shame. Oh, here you go. This one updated. Okay, this one updated. But what about this one? Oh, okay, now it did it. It's a little bit slow to update it. Okay, the parabola downwards, the downward parabola. Let's put x not equal to 0, right? Let's put v not equal to 0. Here you go. The slope here, the t equal to 0 is 0, right? Now it's doing everything it's supposed to do. Positive, here you go. like that. Another one is steeper. See that? The slope here at the point at t equal to 0 becomes steeper. If I change it x naught to 1 meter, it's going to change. This guy here is not displaying every value because I don't have enough, okay? Enough decimals. Now I have it. Now you can distinguish it, right? And so on. Okay. And like I said, if you set up something like that in Excel, you can come up with all sorts of graphs, position versus time. And if Excel is behaving, the way it's supposed to behave, it's going to update your equation and your graph every time that you change anything here. Okay, and 50. So we did everything that we want to do for this example. Okay, let's come up with a summary what we have done so far. Okay. Plot, see, for the plots, see video, last video. Okay. Right here. So what we did so far. We did the following. One, determine equations of motion for uniform acceleration. Right? Uniform acceleration. Plotted the genetic graphs for the equations of motion. Work in an example. Okay, and let's take a look at the book. I want to show you where we are in the book right now. Login. Okay, let's see if it's logged into the website. It's taking too long. Huh? Let's stop it. I'm gonna try it for another page. Wiley plus. No, see, it's true. Trying to log in. Log in. Huh. Still doing it and get on the join into live. Why is it doing that? I don't want that. Ay, 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 ay. Here. Now, let's try it again. Okay, good. Let's see if it's gonna go. I want to try to get the textbook, but it looks like it's not working. I do not know why. We leave it for another opportunity, okay? So let's continue with our. Okay. So what I'm going to do, I'm going to summarize here. Summary of the plots of the equation of the equations of motion, right? One, if A greater than 0, comma, plot of A versus T looks like a line parallel to the T axis above the origin, right? And then we can repeat, if A greater than 0, plot of V versus T looks like a line with a positive slope. With a positive slope, okay? If, right, now here we go. V not greater than 0. If V not greater than 0, the intercept is located above the origin, right? If V naught less than 0, the intercept is located below the origin. If no, if V not equal to 0, the intercept passes through the origin, like that. Okay? And then I'm going to do for X. If A greater than 0, plot of X versus T looks like a parabola with an upward concavity, right? It's an upward concavity, not a positive slope. If, you go, if X naught greater than 0, the graph intercepts the vertical axis above the origin, right? If X naught less than 0, the graph intercepts the vertical axis below the origin. Okay, the graph intercepts the vertical axis at t equal to 0, right? Let me just emphasize that for, not at, but for t equal to 0. For t equal to 0, below the origin. If X naught is equal to 0, the graph intercepts the origin. Okay, or let's see, the graph passes through the origin. I want to even elaborate. Let's see if I can do something better here. Not the graph intercept, but the graph intercept. Yeah, let's do it this way. Yeah, let's do it this way. Okay. Now there's more. There's more. See how we're gonna do that. You go if v greater than 0, comma. No, not v greater than 0. Then if v not greater than 0. Let's see. I'm not gonna do it this way. Let's organize it in a better way. Let's do it this way. If v naught greater than 0, the slope of the graph at t equal to 0 is positive, right? Go this way. If v naught less than 0, the slope of the graph at t equal to 0 is negative. Finally, the last one, if v naught is equal to 0, the slope of graph at t equal is horizontal, like that. Okay? So that's a summary of every possible graph that you can have. Okay? Oh, wait a minute, we still have no, we still have a less than 0, right? It's not every possible graph, it's just half of them. Now we gotta do for a less than 0. Here you go. And the plot of a versus t looks like a parallel line, a line parallel to the x below the origin, like that. If a less than 0, plot of v versus t looks like a line with a negative slope. Then we have the other possibilities, right? We gotta worry about v naught. If v naught is greater than 0, the intercept of the line, right? Of the line is located above the origin. Is located, intercept of the line is located below the origin. The intercept of the line, let's see, the line passes through the origin. I don't need to put that. Here you go, better. The line passes through the origin. The line passes through the origin. If a less than 0, plot of x versus t looks like a parabola with a downward concavity. Okay, and let's see. And now we don't have to change anything here, right? If x not greater than 0, the graph intercept the vertical axis above the origin. Yeah, no change here. If v naught is greater, yeah, no change here either. The slope of the graph is positive. The slope of the graph at t equal to 0 is negative. The slope of the graph at t equal to 0 is horizontal. Okay, so those are all possibilities that you're going to see for uniform accelerated motion. Okay, some of the plots of the equation for uniformly accelerated motion. Huh. Yeah, okay. Thank you for letting me know, Eric. Anybody else had a problem logging into Wiley Plus? Let's see if it's still invalid email password. Wow, I don't know why. Anybody else had a problem with Wiley Plus today? Eric told us, shared with us that he also had the same problem, right? Let me know if you folk anyone had any problems. And 11:05, we might want to go for another break, right? And here you go. Nope, not this one. This one here. Break 11:05. 5 to a.m. to 11:20 a.m. Okay. So I see you in the next 15 minutes. Okay, I'm back here. Okay, so you can see that sometimes we cannot fit a nice parabola using PowerPoint, right? So you have to use other softwares or other techniques to get a better plot. So what else you have to know? Okay, so going back here to our notes, okay? So now you know the following. One, in a graph of x versus t, comma, a, the slope of the graph is the slope of the graph at a given point, is the instantaneous velocity of the object at that instant of time. And B, the concavity of the graph indicates whether the acceleration is positive, concavity upwards, or negative, concavity downwards, but downwards, right? Like that, upwards. Okay, in a graph X versus T. Okay, and now let's go. There's more in a graph V versus T. Okay, the slope of the curve or line, right, is the acceleration. Okay, the value of the slope of the curve or line is the acceleration. Okay, you gotta know that, but there's more. There's one more thing here, right? So let me show you the next. Okay, and in a way I discussed that before, right? Let's see if I can. Oh yeah, right in here. X versus t, right? Here you go. X versus t. The slope of this line at any point here coincides with the velocity. What I didn't tell you is that in a graph v versus t, right? Something is similar. We have something similar. Let's illustrate a genetic graph for v versus t. And this time I'm going to come up with a better drawing here. Yeah, let's use this one here. Now put v here. V meters per second versus t. The slope of the tangent at a given point in a v versus, and I'm going to italicize, right? V versus t graph is the instantaneous acceleration. Okay? Like that. But there is more. It's not just that. Not just that. We're talking about just the slope. But you can also extract the information about the area below a curve, okay? And that's what this next illustration is all about. In the area below the curve in a V versus T graph, okay? Again, let's put italicized here. Is the displacement delta x, okay? What you see here, it has to be a generic curve, okay? It doesn't have to be a straight line. Similarly, if you have a graph of the acceleration versus t, the area below this line is going to be now delta v. Can you remember that? Simple enough, right? So here you go. I have right in here this graph, right? This graph that you see right in here, for this specific case, the area, let me get this area here. The area below this graph that you see right here, gonna be lots of work too. Let's see if I can do better than that. Yeah, no. You know, I think I can do better than that. Let me add a minute. I'm gonna get something else here. Here you go. The area below this line, I'm gonna make this line black so you can distinguish the area below this line that you see right here. And let me put it lower, like that. Huh? Yeah, the area that you see right in here for uniform accelerated motion is nothing but delta v. Is nothing but delta v. All right. And I gotta do something better. Come on, uniform. Right in here. Texture. Let's see. Must be. Let's see if I can get a better filling here. Filling element. More textures. Yeah, doesn't look like they have others. So, texture, yeah, gradient. Nope, they don't have it. Strange. Yeah, okay, but they don't have it. Okay, so the area below this line between this instant of time and this other instant of time, and I'm going to be, yeah, for some reason, I wanted a better filling in there. Let's say between T1, right? And T2. And T2. And T2 represents delta V. And we can have the same thing for the V versus T graph. Let's get the V versus T graph here. Okay. V versus T graph. Let's see if I can get that. Nope, not this one. The area, again, just like the other one, the area below this line. Okay. There's nothing but, I'm gonna fill it up. Here you go. Area. And then I'm gonna add a triangle now. Let's see if I can get fit a triangle here. Yep, I managed to fit a triangle here. The area below this graph. Coincides with what? It's like you saw before. Coincide with delta x. I want to eliminate this. Okay. Okay, better now. Should be something else. Okay, now it's better. Okay. Now we got it. We got it right now. Okay. And oops. Good. Yeah. Remember that? Can you remember that? Oh, going back to my notes here. If this slope of a V of an X versus T graph of an X versus T graph indicates the instantaneous velocity, comma, the area below a V versus T graph gives you the displacement. Okay. Similarly, if the slope of a V versus T graph indicates the instantaneous acceleration, the area below a versus T graph gives you delta V. Delta V. Okay? Like that. And it all comes from the definition that we saw before, okay? And I'm going to get that definition here for you. Remember the definition of average velocity and average acceleration, okay? So here you go. Average velocity is delta x over delta t, right? And then we can here write that delta x is equal to average velocity versus delta t. So if you do not remember that, if you do not remember what I wrote above, just refer to this equation, and you'll be able to remember that. Okay. So the moment that you plot v versus t, the area below this graph v versus t is going to be delta x. Okay, like that. And then the same apply for the definition of the acceleration, delta v over delta t. Here is delta v, here's, it follows the same formula, right? In a graph of A versus T, the area below the graph corresponds to delta V. It comes exactly from this equation here, on those two equations here. Okay? So here you go. I want to write it. Summarizing, you know. One is slope of a V versus T graph is the instantaneous acceleration. The area below a V versus T graph is the displacement. Okay? The slope of x versus t graph is the instantaneous velocity. The area below an x versus t graph is what? Is delta v. Right here. Is delta v. The slope goes up. Okay, go v versus t. Let's see. Oh man, let's see. Delta x is the displacement. Okay, that's right. T goes down. Okay, v. The slope, just remember, slope goes up. Okay, what do I mean slope goes up? V, the slope of v versus t is a, right? Is the next one in line. The area, when it goes for the area, it goes down. V, you get delta x displacement. And here shouldn't be like that, right? The area is not okay. It's a versus t, okay? It's a versus t. You get delta v. Like that. You slope up, area down. Huh? Can you remember that? So this something goes like that. X, V, and A, right? In a graph of X versus T, the slope is the velocity. So the slope goes up. You're going up from X to A, right? That's the progression, right? First is X, then V, then A. Similarly, the slope goes up. In a plot V versus T, the slope is going to be the acceleration. Now, what about the area of A versus T? You go down, right? Area go down, so you end up with delta V. In a graph of V versus T, the area below the line, area goes down, we get delta X, right? The slope up, area down. Let's see if we can put let's put a table here. And let's see, X versus T. Where am I missing the table? Oh gosh, that's not what I want. Good. Let's try it right here. Okay, good. Slope area. Good, like that. Okay. X versus X versus T. V. Oh, I hate that when that do it. I'm gonna put some dots here. X. Okay. X versus T. 1, 2, 3. V versus T. Not here. A versus T. Okay. Slope area. Okay. Slope is V. Of this graph is going to be A, not applicable. It's something we're not going to study, not applicable. Okay. Applicable. The area below X versus T is not applicable. The area below V versus T is displacement. Delta X. Symbol. The area below A versus T is delta V. Okay. Area. And I'm gonna put NA to everything here is going to be center justified. So you can do come up with a table that's more compact, right? Don't forget, the slope goes up. I'm gonna put one more. I'm gonna put one more table here. Direction, right? Up, down, right? Up means, what does it mean? If it's X versus T, up means V. If V versus T, up means A. If it's X versus T, if it's V versus T, down means delta X. If it's A versus T, down means delta V. In the following progression, progression is X, V, and A. And A. That's the progression. The slope goes up, area goes down. Very good mnemonic way of remembering that in case you forget. Another way to remember is to look at those equations here for the area, right? And for the slope, look at the equation here for the ratio. The slope is nothing but a ratio, right? The ratio of delta x over delta t is a velocity. The ratio of delta v over delta t is an acceleration. Okay, so let's see if we have anything else for that. 11:45, right? I'm going to show you some motion diagrams as well. We can do motion diagrams. Motion diagrams are a way to represent a type of motion. Okay, so let me show you motion diagrams now. and I'm going to show you, we can do a motion diagram in Excel, or you can go in the internet. Let's see, motion diagram. Let's see if they have a good motion diagram here in this. Oh yeah, they do. Motion diagram, let's see. Yeah, okay. Here is one motion diagram. I don't like those arrows that they put here, but suppose that this particle, the blue dot here is a particle that's moving, right? If the particle is moving with constant velocity, and assume that you are taking a snapshot at constant instant of time, right? Just like a video camera. A video camera is nothing but several static pictures. That's where the name of movie comes from, right? Movie comes from the expression moving pictures, right? That's where the word movie comes from moving pictures. So that's what we have. We have moving pictures at a given instant of time. This red dot is here, here, here. The only thing I don't get like this representation is those green arrows here. Gets in the way. Okay. So that's what a motion diagram looks like. The particles are evenly spaced whenever the particle is moving with constant velocity. But if it's not a constant velocity, is accelerated motion, right? The distances keep on increasing little by little. I have my own motion diagram that I did in Excel. Okay, so here you go. I'm going to copy and paste here for you to see. Motion diagrams. For uniform motion, the distances between dots, remember, this is a moving picture, right? This is a movie or a moving picture. The distances are equally spaced. What we have here is the x-axis. Okay. That would be velocity be 1 meter per second, and the time separation between each consecutive dot is half of a second. From here to here is half a second. From here to here is half of a second. So consequently, it must be half meter, half meter. If it's half meter, then the velocity is 1 meter per second, right? And here is a motion diagram for a particle undergoing uniformly accelerated motion. The acceleration in this case is 1 meter per second squared. The time separation between each consecutive dot is half of a second, right? It starts at 0. At half second later, the particle is here. It didn't move much, okay? It moved what? Half AT squared. Half second is 0.25. Half AT, right? It's 1 meter per second squared. Let's not forget V naught is equal to 0. I gotta make sure that I write down X naught is equal to 0, V naught is equal to 0, and A equal to 1 meter per second square. Okay, here is the same thing, V equal to, and I'm gonna put X naught equal to 0, right? X naught equal to 0, and V equal to 1 meter per second. So note that the distances increases because the velocity is increasing, right? For every half a second, the distance between those points increases because the velocity is increasing. That's what we have as well. And I'm going to summarize what we did so far. We defined average velocity. We defined instantaneous velocity. I spelled out the equations of motion for constant velocity. I show you the definition of average acceleration, the definition of instantaneous acceleration, And by the way, we also have graphs here for constant velocity, right? Uniform motion, v versus t and x versus t, right? Two graphs. Here we have three graphs. Velocity is constant, acceleration is constant, and we did motion diagrams. Oh, there is one more thing that we have to do. Let's see if we can do that in 10 minutes. Okay, there is one more equation. There is one more important equation for a uniformly accelerated motion. Uniformly accelerated motion. UAM, right? That can be derived from the other four equations. And the other four equations, what do I mean? Other four equations. I mean that right here. Those four equations. The three equations of motion and this important definition that you have, which by the way, is also delta x over delta t, right? Okay, this other important equation, also referred as the Torricelli equation, relates the final velocity with the displacement, the initial velocity, and the acceleration. By the way, this equation is independent of t, okay? It's independent of t, but it's still important because oftentimes we need to find the final velocity from the other three parameters that I mentioned here. Delta x, p naught, and a. Let's see how we derive that. I want you to learn that. What we have to do, we want to eliminate t from the final equation. That's what we want to do. This equation is independent of t. So what we want to do, we want to eliminate this t here in this equation as well as this t here in this equation to get another equation that doesn't involve t. That's the Torricelli equation. Okay? And by the way, I'm not going to use this equation. It's not necessary. All I'm going to do is to use those two here. That's it. And it's implicit from those two equations that we are using this one as well. Okay? So first step, eliminate t from the above system of equations. And by eliminating t, we mean what do we mean by eliminating t? Eliminating t, means that we must write t in terms of the other parameters, okay? That's what we mean. And all we need is those two equations. Because those are the equations those are the only two equations that has t right in here. So I'm going to eliminate t. I can either, write down t in terms of a second order equation, right? Remember? Ax squared plus bx plus c equal to 0. We solve for x, we get the square root. Or we do something simpler. We either obtain the values of t from this equation, or we obtain the values of t from this equation here, which is a linear equation, far easier to deal with than this other one. And so what do we do? All we have to do is, we do the much simpler approach, which is using the linear equation. In the next step, we divide that by a. Okay, like that. Like that. And now we can substitute that right here. And when we substitute that right here, we get what we call, right? The Torricelli equation. Tá chovendo não, tá? Barulho esse. Like that. Let's develop it further. Let's see if we can simplify anything here. V naught V, V naught V naught. And you know what happens when you multiply V naught by itself, right? This guy is gonna become squared when we expand the square here. V squared minus 2v naught, and then finally plus v naught is squared. 1157, we are almost there, right? We don't need the square here anymore. A cancel out with A. Okay. This V square. Let's see what we can do here. Then let's see if we can combine those two now, right? I need another line here to do that. Here we go. So what I have to do, I have to divide and multiply this term here for 2. So they have the same denominator, right? And I'm going to here, right? I'm going to take away this half and just put the 2a there. And now that they both have the same denominator, we can combine the denominators here. And let's see, can we make any simplifications? Look at the simplification that we can make. We have this guy here that can cancel out this other one here, right? That's one simplification that we can do, right? So we are going to cancel out this one with this one. And on the top of that, we can raise V naught to the square. That's another simplification that you can do. To make. And combine this minus 2v naught with this plus 2v naught. When we combine the minus 2v naught with plus 2v naught, we are almost there. Almost there. 12 noon, huh? We're almost there. So let's finish here. I'm gonna pass the X naught to the other side. I have an equal sign here. I'm gonna move this minus B naught to the other side in the numerator. Okay. In the numerator. And finally, we get the following result. Ah, by the way, I'm gonna put the 2A on the other side right in here. Okay, 2A. And we finally have the Torricelli equation. Okay, so we usually write the Torricelli equation this following way, V naught square plus 2A delta X. Delta X. That's how you usually write that down, and that's why I'm gonna put it here. You go. So that's the Torricelli equation. Okay, we're over right now. Right now it looks like I cover almost everything, and we will meet again on Wednesday. Okay. Any questions before we go?
Professor, are you going to stay here until like the office hour is over?
Yeah.
Oh, okay, I have some questions to ask.
Okay. Okay, so let me stop the recording and stop sharing. Recording.